Now let's consider what would happen if we have a loop of current. So we've got some kind of wire that's shaped into you can't really be shaped into a closed loop if you don't have a current, but it's almost a closed loop, and it might go off here and connect to a battery, but we can get it so that it essentially functions as a closed loop. Right? And let's say that there's some current going this way, counterclockwise around the loop. That's our current, and we've got a B field pointing to the right. Well, let's consider what happens. The force on the top and bottom, well, we've got a current that's flowing in the same direction as the B field. They're both to the left, and because they're in the same direction, that the force on the top and bottom are both 0. Okay? And we can use our right-hand rule to figure out the forces acting on the right and left sides. The force on the right, it's equal to IL cross B, the magnitude of which is ILB because they're at right angles, and the direction is downward, into the page. So the force on the right is acting into the page. If we look at the left wire, the magnitude of that is also ILB, but that force, if we follow our right-hand rule, we've got going downward, curl fingers in the direction of the B field, and that is a force coming out of the page. So the force in the left guy is coming out of the page. So if we shift our brains, look at this from a top view, we're looking down on the loop, it's a rectangle, so looking straight down on it, it'll look like a straight line. This force that is coming out of the page then means that we've got a force going this way. This force into the page, again from the top view, means we've got a force going this way. This is the left force, this is the right force, which means that we have some net torque acting on our loop. Okay? Then the question becomes, how much torque? Well, let's say this is a square of length with sides of length L. Then the force is our ILB. And our torque then, our total torque, these torques are both pointing in the counterclockwise direction, which we call out of the page, according to our right-hand rule. So the total torque is FR times this distance from a pivot arm plus the left one times its distance from a pivot arm. If we consider our pivot point to be in the middle, then that distance, the forces are both ILB, and that distance, we can say, is the length from here to here. Actually, I'm going to say this is a rectangle, so this is our length, that can be a width, and then that's times width over 2. The distance is a width over 2, because it's halfway along that top width, and so the total torque acting on this loop in the B field is ILBW, because if you add together 2 halves, you get a 1, right? Well, this length times width is just an area, and in general, if, for example, instead of being aligned in directly the same direction as the B field, if we turn our loop, so it's like this, our forces are still like this, then the angle that they're making, that this thing is making to the horizontal, the torque is proportional to the sine of that angle. So in general, the total torque acting on this current loop is IAB sine theta, or IA cross B, where this B is an area vector that points out perpendicular to our loop of current. Now, what would happen if instead of just doing one loop around, we were to go around and then do a second loop, and then after the second loop we go back and connect it? Well, this is the same, if it's in the same shape, pretend it's in the same shape. you always have to use your imagination when I draw things. If they're in the same shape, then there will be the same forces acting on that second loop that there were on the first loop, and so then if there was a second loop, then the total torque would just double. So in general, if you have n loops, then the total torque acting is just the torque that we got already times n, which would be IA B sine theta times n, the number of windings. Okay. In practice, when you're utilizing magnetic torque, it's typical that you would want to produce as much torque as possible. And the reason for that is that this is used in things like electric motors to convert that magnetic energy, convert the energy in the magnetic field into mechanical work. And so if you want mechanical work, you want as much twisting motion as you can get. And we'll talk a little bit more about how motors work a little bit later on. Another application of this is what's called a galvanometer. And it's something that's used to measure current. It's actually the same basic principle that our ammeters work by. Inside there's a little current loop, and the torque on that current loop causes it to twist, and that twisting motion causes the needle in the ammeter to turn and point to wherever it points to. And the reason that then if you have more windings in the coil, then you're able to there's more torque produced, and so you can measure currents to greater accuracy. The same is true of the needle being longer, because if you have a needle that's yay long, you can have marks on your instrument that are equally spaced, that are this far apart. But if you make your needle longer, you can distinguish between things that correspond to a smaller shift in angle, because then there's a greater distance between those points. So that's an application of that particular example. One other point of note is that this torque equation, we derived this for a rectangle, but it turns out that this works for any shape. This is the torque on any current loop in a magnetic field. This is just the area. It doesn't matter what kind of shape it is. It could be a circle, it could be a square, it could be a icosagon, 20-sided thingo. It doesn't actually matter. So if you're given a current, an area, a B field, even an angle, and a number of windings, then you can calculate torque.